Thank you, Elaine, and all the organizers. It's really great to come here 9 a.m. Saturday night and see so many other people here as well. So I'm currently the VP of Data Science and Machine Learning and Data Engineering at Shopify, but what does that mean, actually? So how many of you here have heard any of the terms data science, machine learning, AI over the last 12 months? Good. How many of you have heard it every single day for the past month? Awesome. So as you know, there's a lot of chatter going on in the space. The field is new in its current format, especially data science. As you can see, the trend has been growing exponentially over the last few years. There's opportunity to do really impactful and creative work, and the demand for skills in this domain has been growing rapidly over the past few years, and there's sort of a shortage of talent. There's also a huge economic opportunity. Last year, I think PwC reported that AI will drive GDP gains of 15.7 trillion. So for me, 15.7 had no sense, so I asked how much was the GDP of Canada last year, and it was around 1.36. So it's close to 15 times what Canada produced is the opportunity out there for us to use these new technologies. Now, as you can see, the third related search query for data science is Python. So Python has become more or less the de facto language of the data science. And the Python community, all of you, have been really generous with your time and effort to push data science forward. So thank you. Myself and my team of over 200 data scientists and data engineers use Python every single day, and we've been doing that for the past 5 years. On the right-hand side, you can see Francoise, which is one of the tech leads on our team, speaking at Montreal Python. So my hope for this talk is to sort of encourage more people to bring their skills to this field, because I think everyone can benefit from that, and also to demystify some of the facts for some people that maybe are starting or want to do more. I'm going to do it in 3 chapters. First about becoming a data scientist, then building teams of data science, because it definitely is a team sport, and then bringing it into products and scaling it as a technology. Cool. So I was not a programmer wizard when I was 7, or when I was 14, or when I was 16. I loved math and problem solving, and when I eventually got introduced to programming, I thought it was really fascinating. So studying computer science for an undergrad sounded like a very good idea for me. And towards the end of my undergrad, I realized that what I was passionate about was taking data science, computation, and everything to other domains and use my knowledge there. Quite randomly, there was a conference about bioinformatics in my university, and they had free food. So I walked over. Most good decisions in life start with free food. So I learned about the field of bioinformatics. Sort of the short definition of it is using computer science, statistics, and math to solve biological systems problems. And I joined McGill University to do a master's there. And as part of my degree, I joined a lab where I was lucky enough to work side by side with molecular oncologists and biologists. My specific project was to use microarray data to predict the outcome of cancer. So microarray, think of it as this concept of a lab on a chip, where you have basically a representation of every gene, and you try to see which genes are expressed under what conditions, and if you can learn anything by that. So the goal of the project was to take this data set and be able to say if at the onset of diagnosis of breast cancer, we can tell if someone is going to have a recurrence in the next 5 years. Now, why does that matter? Because it allows you to pick better treatments and sort of not give too hard of a treatment to someone who's not going to have recurrence, or choose better remedies early on for people that are likely to recur. So that sounds pretty fancy. I spent the first 6 months of my research doing what many people dread. I dreaded it at the time because I didn't really know the value, and that was cleaning up data. So data was coming from our own lab in McGill. It was coming from other researchers that were publishing. And there wasn't a sort of agreed upon format or agreed upon way of cleaning data. So if you wanted to take your results and see if it works on other data sets, you basically had to go through this process of normalizing data. So first few times I was like, oh, I'm just going to do a script because it's going to be quick. But by the time you do it for 10 data sets, you're like, okay, I should probably invest in having a better pipeline for this. And I think the love of good tools for data cleaning has been with me since then. So I tried various algorithms for selecting features, selecting which genes would be good to go on the predictor. And I used different predictive models to see how I can combine them. And I got this predictor that I was super proud of. So on the rows are the genes, and the columns are the level of expression of each gene, and the clinical variables are on the bottom. So I organized a meeting with my collaborators. I was super happy. I was telling them about the techniques I used. I told them about the accuracy of the predictor, all the metrics that you can get out of a confusion matrix. But like within 1 minute, I could see the light in their eyes sort of dim. And one of them, that was the kindest, stopped me and said, so just a second, what do those genes do? And I was like, very good question. I had no idea. So the data points were all correct, right? Like the numbers were correct, but the meaning of the numbers, I didn't understand. And I think I realized that, okay, no matter how good my techniques are or how beautiful those accuracy or those ROC curves are, if I can't explain what I have done in a language that other people that have to use it understand, in a sense, what I've done is sort of useless. I distinctly remember this meeting because I'm always really grateful that they didn't walk out, but the reality was like halfway through you would see that they're not getting anything out of it, and they were like, okay, I guess you're doing this exercise for yourself. And that's like a lesson that has been with me since then, is that I was really focused on the parts of the problem that were really interesting to me. You know, I was like really happy that I get to try all these algorithms and see how they work and how they perform. But for interdisciplinary work to be useful, you actually have to be able to speak the language of people that you're collaborating with. Otherwise, you always would remain the sort of like maybe interesting nerd in the room, but can't communicate with anybody else. And unless people can understand what you have built, they are not going to trust it and use it. So afterwards, I think that has been something that I have kept in mind, is like you have to think about this level of translation in your communication, when you take the results and tell someone, like, why should they care about it? So I went back, I spent 3-4 months going through PubMed, working closely with the experts that, as I said in the beginning, were sitting beside me to understand the meaning of these genes. I was able to say, okay, the top ones are coming from immune pathway, and the bottom ones are from cell signaling. And that you could see, like, people would be like, oh, okay, makes sense. And then we published it, it was good, awesome. So after this, I was like, okay, you know, I've had publications, I can code fairly well, I know math and statistics, and I have got this bug that allows, I get joy out of sort of like tracing stories and curiosity through data. I think one of the best parts of data science is that it's actually less about tools and more about what you can do. It's about having a question and being able to use whatever tools are in your hand and you're capable of using to answer those questions. In a sense, it's becoming a data detective. So super happy, ready to go to the job market. And that was around 2011. Unfortunately, not many people were hiring data scientists then. I remember going to a career fair, and I had like copies of my CV, and everyone was like, oh, data scientist, bioinformatics, no, what does that mean? But, oh, you can program. Cool, there's always jobs for programmers. And that's why I put the title of the talk as a random walk instead of a career path. Because I think when you say career path, everyone thinks I sat there and I had this elaborate step-by-step guide of how to do what I want. Where more so it's sort of a random walk. It depends on chance. And also what, you know, it's not like what happens to you, but what you do when something happens to you. So I took a job in Morgan Stanley. I was really happy working there for a couple years. And then I learned about this hackathon that was happening in Ottawa. So a Friday night, I drove 2 hours from Montreal to Ottawa. I went to this hackathon called Random Hacks of Kindness. And it was, basically, it still happens every year. It's quite nice if you want to join. And it's for people to lend sort of their technical expertise to non-for-profit sector. And we actually use Python for solving the problem there. But Shopify was also one of the sponsors. So through going to that event, I learned about Shopify, I met a few people, and then as a result, in about a month after that, I started working at Shopify. So Shopify is a commerce platform. For those who don't know it, it allows people to sell online, offline, on social channels. We are a Canadian company. We're in Ottawa, Toronto, Montreal, all of that. And despite Popular Brief, we don't just use Ruby. We are also a heavy Python shop in our data science side. So by that time, I was comfortable in the tools of data science, and I knew enough to sort of unblock myself and learn more. So when I joined Shopify, armed with sort of experiences that I had in the rest of my training and what I had learned in my last job, we realized that it's time to build data science teams. And that's what I've been doing over the last 5 years. So data science, as I said, in its current format, is a fairly new field. So these are the things I have learned building teams. First one is actually take a chance on others. So the field is fairly new. No one knows it all. I mean, it was a running joke in Shopify in 2013 that we should look for someone with 10 years of Spark experience. So not many people have done most of it for years, and also there's every 3 months there's a new Venn diagram with a set of skills you need to master to be called a data scientist. When we started going through interviews and trying to find people that were able to do everything, we realized that actually that's a very unrealistic expectation and might not even result to very strong teams. What we learned was to sort of agree on a few things that were important for us and go from there. For example, for me personally, the level of sort of self-awareness of someone knowing what they are good in and what they are not good in is one of the key things. Another one is their ability to learn, because I think with the two hand in hand, they understand what they don't know, you can support them, they learn, and it goes on, rather than focusing on the skills that someone has right off the bat. One of my best hires is someone who came to our interview process. He had just moved to Canada, and he said, I have just finished school, I don't know much Python, I'm learning, but I'm really good in SQL. Would you take me as an intern? And if it works out in 3 months, you can hire me, and if not, that's okay too. And for me, it was really important because this person was very clear on what they knew and also very confident in what they can learn. And now they actually lead our shipping algorithms team with 7 people, do many, many amazing things. Another one is that data scientists come in all shapes and forms. Not many universities have track record of producing data scientists, and even if you come with a degree of data science, the experience is really important. So what we realized was that, what are other fields where people have to deal with messy data, lots of statistics, and make conclusions? And then all of a sudden, the total addressable market grew by orders of magnitude. Physicists, astrophysicists, economists, all of these people have to deal with data, make meaning out of it, and then they can be called data scientists. And you can help them sort of pick up programming skills or wherever they are not strong. This also has allowed us to sort of build a data team that's really diverse in the way we think. I challenge you to sit with an economist and a mathematician and a physicist and just listen to the discussions. You learn a lot, and you also see the world from a very different perspective. The other reason that it's good to have sort of this diverse teams in terms of skill sets and personalities is that data science is one word, but the actual work is quite extensive. So there is this famous hierarchy of needs in AI and data science done by Monica Rogati. She's one of my favorite data scientists. And it goes and talks about sort of different levels of skill and capabilities that a system has to have before you can do data science. So most of the chatter we hear is on the top of that pyramid. It's around AI, deep learning, machine learning, whatever flavor you want to call it, maybe a little bit simple algorithms. But the reality is that without the basis, without being able to collect the data, without being able to move and store it or explore it to see what the data is showing you, you cannot go beyond that and build the other stuff in a scalable and for the long term. And I think accepting this and being quite honest with the candidates about it is actually one of our success stories. When we interview people, we tell them hey, all of these are things that we would help you, we would support you to learn. But all of these also need to be done. We don't have any roles for people just to sit on the top of the pyramid or just to the bottom. And that has actually allowed us to have very very good teams. So the quality of and speed of data science work relies heavily on how strong the foundations are. Each level of pyramid, basically the quality of each level of pyramid is solely dependent on what you have underneath. And we actually went through this firsthand. So in 2013, we had this tiny data warehouse built on Ruby on Rails and was loading into Vertica. And we saw that as the company was growing and the need for data was expanding, we needed to change that. First of all, the technology was not expanding as fast as we were. Sorry, like that technology for that use case was not moving as fast as we needed. While Ruby was something that most of our company at the time had experience with, it was actually didn't lend itself well to data science, and there was like lots of other options out there. So we actually rewrote our entire data warehouse in Python and Spark. It was a very interesting journey because 2013, not only we didn't know how to make the joins work in Spark, the internet did not know how to make the joins work in Spark. So we went through a lot, we figured it out, and I think as a team we actually became much stronger, but also as a data team within Shopify, we became a team that was relied heavily upon because we could talk about stats and numbers and story behind data in a way that was reliable, in a way that was reproducible and like explainable. There is nothing worse than two people going to an executive and reporting two different numbers for the same metric, because as a result, they're going to trust none of them. So going through this journey actually like crystallized why you should have like clear definition, you know, all these boring stuff, but are actually really important. And if you do them beautifully, you look at a data set and you have this like joy. It's so good, it's so clean, I can recreate everything to the same standard. And actually having that in place allowed us to be able to go, was one of the factors allowing us to go public in 2015. So all of the analysis of any non-GAAP metric that you see in our filing, in our roadshow, they have all come out of the data science team. And we have been able to sort of like help tell the story of the company through numbers since then. So while all of this was good and nice, we also realized that having this clean data assets have allowed us to sort of like now create experiences based on data. So end of 2015, data team had got a reputation that, you know, these guys know their stuff and they can do it with a high quality. So Shopify was embarking on a new product called Shopify Capital. So what does it mean? It means that we want to give cash to our merchants to help them grow their business. And we only take money back when they make sales. So if they don't make sales for 2 years, we're not going to see that money back. So it's a very interesting, if you like sort of peel the layers of onion, it becomes a very interesting like math problem on the back end. Basically, you want to be able to predict someone's sales with not only correct numbers, but also correct velocity. You want to be able to say, okay, this person is going to be able to make this much of the money at this point, this much in 6 months, and also bring this concept of probability and taking risk to the finance department. Because now we are giving real good cash to people based on what the models say. It was amazing. We had this product manager, came from a hedge fund, and he like really sat with us, explained the domain to us. And for the first models, we went with sort of like rule-based systems where he was telling us the rules. And little by little, we started to take like portions of portfolio where we only extended offers with machine learning. And as of last year, actually, all of the offers go out with machine learning. And it was really good experience in sort of like gaining the trust, not only in data, but on probabilistic things that can come out of data. So then we had one data product with lots of good stuff in it. You know, every earning calls you would hear about capital. But then how do we take this from one product and bring it across? This is really a passion of mine because when you look outside, when you look on blogs and tutorials and all of that, there's a ton of fantastic material around how to build new machine learning algorithms. The research has been going great. In Canada, we are so lucky. We have like world-class experts in Toronto, Montreal, everywhere. But how do we take that and bring it to industry? Because at the end of the day, the day-to-day life of me and you and everyone would improve as a result of machine learning and AI if the systems are useful, are scalable, and can be used by us. And what I'm going to talk to you looks like we've figured it out. It's a result of like 3 years of work, and it's still a work in progress. And I'm more than happy to answer any questions about it afterwards. So the first step is to actually start very simple. There's a ton of algorithms out there. And I love the landing page of scikit-learn because it has this sort of like flow chart that you say if I want to do prediction, if I want to do forecasting, and it like walks you through how to pick the best algorithms. But the problem shouldn't, like the work shouldn't start from what algorithms you use. We should take a step back and be like, okay, what is the problem that we want to solve? And for that problem, what data do we have available? I know everyone thinks that they have been collecting data for years, but in reality, how much of it is actually accessible? How much of it do you have rights to use for a product? So those are like the first questions that you have to answer. For us in Shopify, one of the next things we went to after Shopify Capital was order risk. We wanted to be able to detect the risk of fraud on every order that goes through our platform. So few reasons we picked it. We've been processing orders for a decade. We have lots of data. But it's also something that all of the merchants have to use, which means we would get feedback and data on their usage quite quickly so we can fix and adapt our models as we go. A good hack for finding out places where you can use this is looking for huge blocks of if then else, or basically rule-based systems. Those are really good first candidates to say, okay, this is somewhere that we can actually get business value by applying machine learning. If you remember one thing from this talk, I want it to be this. What you're doing when bringing machine learning to products, you're not doing an exercise in computer science. You're not doing an exercise in data science. The problem has to be solved from the perspective of the domain. At the end of the day, the users of an app or a software do not care if there's an algorithm on the back end giving them good results or there's a human hand picking things for them. They just want things to work. And that means like the metrics and the focus of the algorithms and the systems should be on users, should be on how users react to these recommendations. How often do they take them? Because at the end of the day, if I show an order is risky, but the merchant doesn't trust anything that I tell them, who cares if I was correct or not? They still have not acted on that recommendation. In many cases, there's also industry benchmarks. So, for example, if you're doing inventory forecasting, the industry knows that, okay, up to 80% accuracy is good enough. So when you build an algorithm, don't shoot for 100%, because then that would take you years to get there, and people would give up on you ever publishing any results. Say, okay, 80 is the base. Can I bring it to 82%? Can I bring it to 85% with a little bit of effort? So pick a problem that you fully understand, that you have data sets for, and then pick metrics that are about the users, how they would interact with your system. And then afterwards, you basically have sort of like a proof of concept. Then it becomes time for fun engineering. One of the things we have learned is that the better your pipelines for machine learning, the faster you're going to have new models out, the better iteration speed. So one of the things we did is, and we've done all of this in Python, of course, as you can see. One of the things we did, we have defined like clear testing and training pipeline. So in the training pipeline, we actually clearly say, okay, this is input data that's coming raw. These are the transformations, and this is how the input that goes to the model. Now, why do I care about it? Because I lived 12 months when I was doing masters trying to remember, did I replace the missing values with nulls in that data set or with 0? And did I do the same across? Oh, and that run of the model that was really good, which version of the code was it running? So while this takes some effort to put in place, I highly recommend putting it there. You can have faster debugging, you can have better model development, and in general, a more pleasant experience for your data scientists. The same thing about testing and verification. Worst thing is presenting some results and someone say, oh, that's really good. Can you tell me what were the accuracy metrics around it? What was the F1 score? And you're like, I have to go see which data set I used and which version of the code I used. So having rich metadata around sort of machine learning pipelines allow you to have reproducible result and also buy trust with your users. And the last one is something I took from finance. So every financial advisor, when they are trying to try a new algorithm on a portfolio, they run it on the last, say, 6 months of the data. to see how that new algorithm, a new model, would act on portfolio compared to the existing one. Say if the old model was putting like 80% of the orders in safe, the new one is doing like 85%. How do these predictions compare? So it's not about like how good the predictions are, but how does the output of the machine learning model compare with each other? That has allowed us to do some cool things. So for example, when we run a model, a new model on a data set, what we do is that we start to slice the predictions based on segments of the audience. So we are able to see like, okay, is there a part of the population that we are highly classifying as fraudulent? And is that true, or is it because we have lots of missing data? For example, if we are looking at credit card data, and in some countries, credit cards are not common, but we've built our models on countries like North American countries where credit card is common. So if we take this model and we run it in a data of a country for evaluation, where there's little credit card, our results are actually, the model is correct, the data is correct, but the results actually mean nothing. So having this concept of backtest has allowed us to sort of like catch things before they go to production. It also allows us to see like, are there users whose experience is going to change significantly as a result of a new model? Say when we bring a new fraud detection model to production, for most merchants it's good. Maybe there are some merchants with edge cases, like super high volume of orders, or super specific segment of buyers, and their experience is gonna completely change. Like till yesterday they had 1% fraudulent orders, today they have 0.5%. Like it's our duty to actually like reach out to them, let them know, because at the end of the day, these models impact real humans, right? It's not just for fun, it's like life of people can actually change based on these. So we have testing, we have training, we have production backtests. What's next? So we actually have to bring these models somewhere inside an application that they can be used. And while there are so many ideas around deployment, there isn't really best practices. It's really dependent on the stack you have and the nature of the problem. Do you need to be real time? Can you serve predictions in batch? But there are questions that you need to answer before you make those decisions. And first one is to plan for volume. The needs of a server or service that has to do evaluation for instances once every day is going to be very different to a server or algorithm that has to emit results like 600,000 times a minute. So for example, for our cash advance, we sort of create these offers in batch, we serve them back to the admin, the merchant picks the cash advance when they want. For order fraud detection, every minute that an order is coming in through the checkout, we have to evaluate it for a risk of fraud right there and then, and we don't want to slow down the downstream dependencies. So the volume here becomes a point that we have to think about. And the other one is, as I said, product SLA needs. So again, in case of order fraud detection, we don't want to slow down checkout. Like checkout is the bread and butter of any e-commerce platform. So if I had gone to our checkout team and said like, oh, we have this amazing machine learning model that can predict fraud with high accuracy, but it would take half an hour for it to come back. They would have been like, okay, good, you can play with that for another year. And those are the things that you have to think about heavily, because so many times I hear people in other companies or like people joining the team say like, oh, I have built this like super amazing algorithm. It goes to like the best accuracy, best performance, but it would take it a long time to provide results. That means, well, at least right now we cannot use it. And those are the questions that if you answer early on, you can have like an MVP in production while you figure out the next steps. So now you have one model in production, but you can't stop there. The data sets change, the basically user's life change, so the data they emit is gonna be different. So you have to think about like, okay, now we have one model, but how can we bring more or next models into life? The first thing is to actually build trust. Because users are super smart, they figure it out before you've even had a chance if a model is acting weird or it doesn't pass the safety checks that they have built in their own mind. So one of the things we have invested heavily on is building this sort of like checks that make sense for our user base, for our stack. One of the things we do is that before a model goes into production, we actually put it in the server, but we run it in what we call shadow mode. So for every order that comes in, the current model is emitting the recommendation, but also the shadow model is emitting to Kafka. And we take these and we see, okay, first of all, is the model in production, in shadow, acting the way we thought it would be in training and testing? How's the SLA? Is it taking too long now that it's running there? And only when these checks have passed, we sort of promote it to powering user experiences. The other thing is that the world around us is constantly changing, right? So that's a generic sentence. But what does that mean in sense of machine learning and data science? If I'm building models based on data that I got from, say, July till September, the user behaviors is one thing. But when we go to, say, Black Friday, Cyber Monday, towards the end of the year, where purchase habits of people are changing, the models, the reality of the world that I'm going to see at that point in time is going to be very different from the time where I built my models. So what can we do? In the beginning, we were like, okay, how can we catch this? How can we know? And maybe not all of the changes are important. So one of the things we did is that before you build all the infrastructure, what we did was we had a job that would check the changes in the distribution of the features, and when they were beyond a certain point, it would pop it into our Slack channel, and the person who was on call would dig and see what's going on. So the point I want to make is you don't have to wait for all of this to be part of this catalog of infrastructure to be able to do them. I think it's important to know the right steps and try to implement them in what you have, because if you lose the trust and everything in the process while you're building the fancy infrastructure, nobody is going to actually be using the software anymore. And then these are the things that we are trying to get better at. Right now we say, okay, we want to deploy new models for some of the products every 2 weeks. So that means that we have to be really good in automatic model deployment. We have to be really good in keeping history and versioning of the models. And we have to sort of be able to see what other downstream effects this training cycle is going to have. And I really would like to learn from others how they do it in their job. But if we had to do this every single day with a small team of data scientists and the shortage of talent, probably we wouldn't be able to move forward. And that's why we spend a lot of time thinking what we can automate. So for us, we have automated most of this. This is sort of what our flow looks like. So we build the models in Python using Python and Spark. Then, because one of the applications where we deploy these models is in Ruby, we needed to find a way to go from Python serialized models to evaluation in Ruby. So we could have said, OK, we're going to spend a year to build a service in Python that can take this, that can deal with the volume, that can do all of the things. Or we could say, you know what, Shopify is really good in Ruby. Maybe we can translate the model into Ruby so that we can give the benefits to the user in the meantime. And that's why we invested in building our own sort of Ruby gem for PMML, which stands for Predictive Modeling Markup Language. So it's like XML for predictive models. It has existed since the 70s. And Python actually has binding. So we can create the models in Python. It translates into PMML. And someone on my team has built a gem that he's going to open source where we can basically evaluate these PMML models in Ruby and then push it to production. And all of this runs on a scheduler with Uzi. So again, nothing out of the ordinary, but just having this workflow has allowed us to move fast. So having the pipelines would allow you to also wash, rinse, and repeat. For any new product that comes in that needs sort of I would say the basic machine learning, nothing out of the ordinary, we can actually use these pipelines. And it has allowed us to scale the existing products. Capital has been in use. Deloitte has called it the fastest growing fintech in Canada. But for me, the best moment was when, on an earnings call, they asked our CFO, so why do you think your cash advance offering is growing so fast? And I said, oh, because we have very good machine learning models and talent in the company. So I was like, yes, we made it. If the CFO can explain it, then that's good. And they often refer to sort of our team as oh, this product uses artificial intelligence or augmented intelligence, which is what we contribute to. For our order fraud, it was very cute. Somebody actually pinged our CEO to thank him personally for being able to detect a couple fraudulent orders. And then we've built more products like Fraud Protect and so on and so forth on top of it. So all of this is pretty fun. And it's really impressive when we see these merchants who are starting in their home or having a small brick and mortar store and their life has gotten better without having to go out and hire their own data scientists. In a sense, we've been able to sort of like take the skill set and now scale it to over 600,000 merchants. They can start their business right off their computer, and they would have insights that are generated with machine learning. They can also have established businesses, and regardless, their experience with this product is going to be good. So, to recap, if you want to become a data scientist, the tools and techniques are a must-know, but I think people would grow once they find a problem that they can be passionate about, and they spend the time to learn about it. I want to be clear, like, maybe you're not passionate about it the moment you hear about it. When I interview people, I say, you want to work on shipping, do you think you can fall in love with shipping? I don't expect you to be in love with shipping before you join. But it's very important to think that, can I be interested in this domain? Does it have enough sort of like, do I have enough curiosity to follow it for this domain? And then when you get to building teams, remember that data science in its current form is very new. So you have to keep your eyes open and sort of accept that experience comes in different forms, and you need different experience for different layers of that pyramid. And last, going from a model with a single use case to many models powering many use cases, you have to start with baby steps and invest heavily in good engineering practices. And with all of that, Shopify is now hiring data scientists, Python engineers, all of that. So I wanted to share the happy sign that I didn't have when I was looking for jobs. And yeah, if you want to talk to any of us, there's a bunch of us here in the audience that we would love to talk to you. And thank you.